Hello, my name is Anton and I will present the paper VerX Safety Verification of Smart Contracts. This paper was done by a team originally from Software Reliability Lab of ETH Zurich. So what are the smart contracts and why they need to be verified? Ethereum is a public blockchain-based application platform, and smart contracts are pieces of code that implement those applications. They often manage high-valued assets and important data. In addition, Ethereum smart contracts and their data are visible to any participant of the network. Bugs, if present, are visible and can be exploited by all, yet there are no native and easy way to quickly fix them, as the design of Ethereum blockchain system does not allow the code of the smart contract to be changed after it has been deployed. Thus, the absence of bugs and errors in deployed code is of utmost importance. One of the ways to prove the absence of bugs is to certify functional correctness of the smart contract. For a given smart contract application, developers can come up with a functional specification and prove that any behavior of the system fits it. Let's take a look at what formal specification can look like. For example, on the left, we see contract time locked that has two Boolean fields, withdraw and refund. There are two functions, withdraw and refund, that depending on a deadline can transfer the balance of contract to either Alice or Bob. There is also a fallback function that can be used to load some balance onto the contract. On the right, we can see a formal specification that's written in natural language that developers can come up with. First is, contract cannot be both withdrawn or refunded. Second is, refund can happen only after the deadline. First, to verify the specification, we need to formalize the requirements. We need to take high-level requirements written in natural language and come up with a formula that will precisely tell us which states of the contract are valid and which are not. So, for a property, contract cannot be both withdrawn and refunded, we can come up with a formula always not withdraw and refunded, where withdraw and refunded are the fields of the contract. This property, you see, actually was written in a VerX specification language that we use. It supports past LTL formulas that have an ability to concisely express useful security properties. So let's take a look what these properties can look like. Here we can see access control property. Smart contracts often implement this to give administrator manager certain privileged access to certain functions. In natural language, this would sound like deposit function cannot be called by owner. Second type of specification is state-based property. They are used to express the general relations between fields and functions of the smart contract. This property in English can be expressed like refunds happen only within 1 week after the refund start time. Next is state machine property. Smart contract often implements this pattern, and with VerX we can check whether the transition from one state to another happens according to the model of a contract. Another kind of invariants we find in code are invariants over aggregates. This invariant is used by most popular Ethereum technical standard ERC20 that standardizes the token contracts on Ethereum. VerX make it possible to track the changes of values in maps and arrays and verifies this property. The last is multi-contract invariants. Developers quite often separate the logic of application into several smart contracts, and with VerX one can specify the whole application. So what does actually VerX do? You have two inputs that we take, smart contract application and formalized specification. As a result of verification, the output can be verified or may not hold. If the output is verified, it means that the specification will hold for any number of transactions for any input arguments. Let's take a look how VerX works. So here we see the smart contract application that consists of two contracts. First contract is escrow contract that implements state machine pattern and has three states: open, success, and refund. It starts in open state and by the owner of the contract can be switched to either success or refund states. The owner of escrow is actually a crowd sale contract. It has two functions. First function is invest function that forwards money to the escrow contract. Second function is a close function that, depending on closing time and the amount of raised funds, can switch the escrow contract to one of the other two states called the refund. Let's look at the specification of this application. So, for example, here we can see specifications that in English is read as investors cannot claim refunds after the crowd sales. goal of either is collected. It has this specification in VerX specification language. And now if we press the verify button, we see that the property was violated, and the trace of violation is initializations, close, crowd sale close function, crowd sale invest function, and a scroll claim refunds function. So we see that this property actually doesn't hold with this violation trace. After we saw how VerX works, let's look in details what challenges we had solved. One of the challenges was the specification challenge we will speak about now. On the left, we see the same tabular contract we saw earlier. On the right, we have a property. This can be expressed as the balance of contract should be 0 after the refund. In case when Alice calls the refund function of the time locked and the requirements are met, the whole balance of the time locked contract will be transferred to Bob, and the balance of time locked will be 0. But this works only assuming that the Bob is not a contract address. In other words, there are no underlying contract deployed at a Bob's address. The design of a zero network is such that any transfer to non-contract address will just increase the ether balance of it without any complications. So, assuming the Bob is not a contract, the property holds. But what about the general case? Problems arise when the contract calls not other user-controlled address, but another contract. If you have a property after the refund the balance of time locked must be 0, and Bob is another contract, the property won't hold. One possible violation trace is shown in the diagram on the right. After the initial call from Alice, the time locked will transfer the funds to Bob. The design of Ethereum is such that during this call, Bob's contract code will be executed. Because this code can be arbitrary, it can transfer back some money to time-locked contract using the fallback function. Thus, even though the topmost call was the refund, the property will not hold as the balance of time-locked will be increased. Here where the specification challenge arises. We had a property that intuitively should hold, but considering the callbacks from external contract, it doesn't. That is a specification challenge that was solved in prior work of Grossman and others from 2018. There was introduced a callback freedom condition. Contract, if fulfills this condition, can be specified if there were no callbacks at all. That condition greatly simplifies the specification complexity for a single contract. But this condition works only for a single contract. In a real-world scenario, where the application implemented using multiple smart contracts and the contracts that belong to the same application call and call back each other all the time, that condition won't work. That's the limitation we managed to overcome in our work. Our contribution is effective external callback freedom. We lifted the attack callback freedom constraints to allow a simple specification of a bundle of contracts, not a single contract. This condition permits the callbacks between the contracts of a bundle, but allows user to consider no external callbacks. Under this condition, the specifications are much smaller and easier to write. Specification process is faster and more intuitive. In addition, the external effective callback freedom condition is satisfied by most real-world Ethereum applications. So far, we looked at the specification challenge. Now, let's look at another challenge, the automated verification challenge. To verify the smart contract application, first, all behaviors of the bundle of the contracts are encoded as a program. We put all the functions into infinite loop, where each iteration of the loop corresponds to a single transaction executed by arbitrary user with arbitrary arguments. The specification becomes the assertions inside the loop. Then, by verifying that this assertion holds, we can prove that the initial specification holds too. For example, we use so far. The encoding will look like you see now below. The spec contract cannot be both refunded and withdrawn will become an assertion, and the body will become arbitrary function execution. To correctly represent the Ethereum behavior, we added there one more function, increment of the current time. The unresolved problem we have now, infinite or very large state space of this program. Let's see how to deal with it. First thing we do to shrink the state space is symbolic execution. we implemented the precise zero bytecode symbolic execution engine that helps us to deal with arbitrary input arguments. One symbolic execution transaction covers all possible input arguments of the function. Now, several states of the initial state space can be represented by a single symbolic state. Next, to shrink the state space even more, we use predicate abstraction. The combination of symbolic execution with predicate abstraction results in significantly smaller state space, where the property can be verified using modern SMT solvers. Let's see how the predicate abstraction will act with our example and predicates that you see on top. With predicate P withdrawn and Q refounded, the abstract state space will consist only of 4 states. The predicate abstraction abstracts the balances of the contract and thus reduces the state space we need to explore now. Now, let's see how symbolic execution works together with predicate abstraction. On the left, on top, we can see green abstract state not P and not Q, and a blue corresponding to its state where withdrawn field is false, refounded field is false, and balance is some symbolic variable x. If we execute fallback function, the function that allows contract to receive money, the withdrawn will stay false, the refounded will stay false, but balances will be increased by some symbolic variable y. If we abstract this field now, it will yield us the same state we started with, not P and not Q. In the middle, we start with the very same abstract state, but execute the refund function. This, if successfully finished, will change the refund field to true, and balances will be sent to some other address, and as a result, the abstraction will yield us the not P and Q state. Rightmost example is similar, but with withdraw function. The withdraw will become true and balance 0. The abstraction of this state will yield us P and not Q. Let's visualize our state space and see how predicate abstraction exactly looks like. The gray area you see here is our full state space. 2 lines, red and blue. Our predicate. Red line is predicate P, withdraw. Blue one is Q, refunded. Each predicate line splits the state space into 2 subspaces, one positive and one negative. The lever circle in the top left corner is the initial state space we get after the constructor execution. Abstraction of the initial state yields us not P and not Q state. From this state, we can discover the P and Q state by executing the refund function. Next, we can discover P and not Q state by executing the withdraw function at the initial abstract state. If we now recall our property, it basically says that our system should not reach the state P and Q. But as we see, by executing the withdraw function from not P and Q state, we actually can reach this state and violate our property. But is it a true violation? The problem we can have with predicate abstraction is the lack of predicates. Let's try add some more predicates. Here we added a new predicate, R. That means now more equals a deadline. This is visualized by a green rectangle in the middle of a picture. The area within the rectangle is a positive subspace of the predicate. Outside area is negative. Initial state will be abstracted to more detailed state, not P, not Q, and not R. By increasing the system time, we can reach new state, not P, not Q, and R. Now, let's look how withdraw and refund functions changing our explored state space. The only state that we need to discover now is that the state we can reach by increasing system time after the withdrawal. Now we can see full reachable state space from the initial state. We can see that the property actually holds, and adding more predicates has helped us. So we present VerX, the tool that can automatically verify temporal properties of infinite state smart contracts. Specification of the bundle of contracts can be now done easier and more intuitive using VerX past LTL specification language and the effective external callback freedom condition. The symbolic execution coupled with predicate abstraction reduce the potentially bounded concrete state space of the contract into finite bounded representation while still maintaining precision. Verification now can be done easier. But VerX is not only the research tool. It was used to verify the contracts that were actually deployed to the Ethereum network. With its help, in some cases the application verification time was reduced down to hours, including the time needed to write the specification.